Welcome to Chapter 7, Section 3, where we're still going to deal with taking or solving differential equations using the Laplace transformation or the Laplace transformation. But here what we're going to do is we're going to see how we can deal with a transformation where we have more than just one function. That way we want to do a Laplace transformation. And one of our functions is going to be an exponential function, and then the other function is going to be either a function such as a polynomial, t squared, t cubed, that sort, or a sine cosine function, or hyperbolic sine, hyperbolic cosine. So in this section, we're going to consider several operational properties of the Laplace transformation that will enable us to build up a more extensive list of transforms without evaluating improper integrals. So what this is it's going to be a trick to where we don't have to deal with complex improper integrals. And so the first one is going to be a translation on the s-axis. So the first translation theorem is if we have a Laplace transformation of a function defined by t, and that's going to give us a function now defined by s, and a is any real number, then what we can say is if we do a Laplace transformation where we have an exponential to a t variable with some constant a times f of t, which is a function of t, then we can say that's just going to be cap f, meaning the Laplace transformation, so cap f of just s minus a. And the reason we can do this is if we have a Laplace transformation where we have e to the at times f of t, and we want to put it in our integral, we put it in the integral e to the negative st times what's inside the Laplace transformation, e to the at times f of t. Well, we can go ahead and combine the exponents. Since it's a common base, we can bring these together by addition, but we want to keep it in the same format where we have e to the negative st. So we're going to have e to the negative and then s minus at. I know if we just added these, it'd be a minus s, but to keep it of the same form, e to the negative some constant times t, we went ahead and wrote e to the negative s minus at, f of t, d of t. When we integrate this, we're going to get cap f of s minus a, which is basically the same integration we would have had when we had e to the negative st times f of t. We got a function defined by a new variable s. Well, now we have a new function defined by the new variable s minus a, where a is still a constant. And if we do this, it's going to make our work much easier. Instead of having to evaluate, this improper integral, all we have to do now is to find out what cap f of s minus a is. And so to do this, we're going to use the following symbolism, where when we have a Laplace transformation with some exponential to some constant times c, which that constant will be a, times f of t, that's going to equal just the Laplace transformation of f of t. And when we do the Laplace transformation, we need to make sure that our s is now defined by s minus a. So once we do the Laplace transformation, anywhere we get s, we need to make sure that we incorporate the s minus a. So this is just the translation on the x-axis. We're just shifting our transformation. We're just shifting that graph over by some a. So example 1, find the Laplace transformation of t e to the 2t. So here we have a function f of t, which is defined by t, times an exponential e to the 2t. And so we have to have that times the exponential in order for this to work. So instead of dealing with t e to the 2t, we're just going to do a Laplace transformation of t, making sure that we define s by s minus 2, because a is our 2. And so s is now s minus 2, which you can see there. And so now, we're just going to do the Laplace transformation of t. If you recall from last section, the Laplace transformation of t is just 1 over s squared. And keeping a reminder that s is just s minus 2, then we can say the Laplace transformation is 1 over s minus 2 squared. And that's it. We're finished. That's the Laplace transformation of t e to the 2t. We're just trying to find, okay, what's the function without the exponential, and then do a Laplace transformation of that, and then make sure that we incorporate back that exponential, which in this case was that minus 2. All right, example 2, Laplace transformation of e to negative 6t times cosine 4t. So again, there's our exponential, so our function is cosine of 4t that we actually want to do the Laplace transformation of. So we do the Laplace transformation of 4t. Remember, that's just s over s squared plus 16. But we have to keep in mind that, hey, our a is negative 6, so it's s minus negative 6 or x plus 6. And so once we do the Laplace transformation of cosine of 4t, which is s over s squared plus 16 again, we're going to substitute in for s plus 6. So s plus 6 over s plus 6 squared plus 16, and that's it. We're finished. So you're going to find that doing the Laplace transformation, using the translation on the x-axis, using this translation, it's making our problems become a little bit, more easier to work with, or more easy to work with. Now, when we're doing the inverse, we want to do, again, we want to flip things. So when we're doing the Laplace transformation, and the inverse Laplace transformation, we're looking at it as if it's f of s minus a. Again, so we're going to be able to notice this by just looking at our function and determining, is there addition and subtraction with our s? If there is, more than likely it was of s minus a. And so what we're going to do is we're just going to do the Laplace transformation of f of s. So going back to last section, we're just going to deal with this, and wherever we have an s, we're going to make sure that we denote, oh hey, that was s minus a, so we're just going to move it's kind of going backwards. We're going to take the s minus a, we're going to go to s, and then it's just going to be e to whatever that a is times f of t. So looking at the first one, the inverse Laplace transformation of 1 over x minus 1, s minus 1 to the 4th. When we're trying to solve for this, we notice, oh, there's addition subtraction with the s that's inside of our power. So we know that, okay, I want to make s minus 1 just s. So s minus 1 is going to be s. And we're going to look at this as 1 over s to the 4th. So when I look at this as 1 over s to the 4th, I'm thinking, well, what should be 1 over s to the 4th? When I go back through my notes, I know that it really should be 3 factorial over s to the 4th. So this 3 factorial I have to introduce. Well, if I'm introducing this 3 factorial, I have to take it out. So 1 over 3 factorial. Now 3 factorial is just 3 times 2 times 1, so 6. And so I have that 6 over 5 fourths, s to the 4th. And so when I do the inverse Laplace transformation of this, it's just going to be it's just going to be t cubed. This 1/6 comes from the 1 over 3 factorial. And then since we have s as s minus 1, I had to have an original e to the t. And so this e to the t comes from this s minus 1. T cubed comes from the 3 factorial over s to the 4th. And 1 over 6 comes from the 1 over 3 factorial because we had to introduce the 3 factorial there. All right, now example 4 is a little bit more complicated than some other problems that we've dealt with because we're going to go back to completing the square, and it's not, you're not going to be able to look at this problem and know exactly what to do right off the bat. And so what we're going to do is we're going to look at our inverse Laplace function. We're going to look on the inside, and you notice there's nothing inside of this s. It's 2s plus 5, s squared plus 6s plus 34. So what we are kind of hoping what we can do is factor the denominator, but the denominator is not factorable. because the denominator is not factorable, we want to complete the square to be able to factor some part of this. And so when we're going to do that, that's when we know, oh hey, I'm going to have to incorporate the translation on the s-axis in order to complete this. And so because this does not factor out evenly, I'm going to complete the square. So s squared plus 6s plus 34. If I look at this, I know that s squared plus 6s, what I really need is a plus 9. So what I can do is I can break this 34 up to be 9 plus 25. If I break up 34 to be plus 9 plus 25, I can factor this by making 6 squared plus 6x plus 9 just s plus 3 squared plus 25. And now I have a s plus 3 squared plus 25, which we can reduce to s squared. Alright. And so we I'm sorry, 5 squared. So s plus 3 squared plus 5 squared. Now, what we're going to do with this is we're going to put this back in the denominator. And so now that I know, hey, I could not solve this just by factoring it because I had to use completing the square, I know that I need to find my s minus a. Well, looking off of this, alright, I know that my a is going to be found by the s plus 3. And so I look at the top, and what I notice about the top is that I have 2s plus 5. I can break the top up to be 2s plus 6 minus 1. Now, why did I want to break the top up to be 2s plus 6 minus 1? Well, the reason I want to break that up is because I want my numerator and my denominator to have some similarities. And I know that if I have an s plus 3 in the denominator, I would like an s plus 3 in the numerator. And so I look, well, hey, I could pull a 2 out of the 2s plus 6, and I can get an s plus 3. So I'm going to do that, and then I'm going to separate my fraction. And so I'm going to have 2 times s plus 3 over s plus 3 squared plus 5 squared minus 1 over s plus 3 squared plus 5 squared. So now, on the left, what I can do is I can notice, hey, I can pull this 2 out, and I can have an s plus 3 over s plus 3 squared plus 5 squared, and do an inverse Laplace transformation of that. And on the right, what I can do is I can put a 5 in the numerator and pull out a 1/5. Now, why would I want to do that and do an inverse Laplace transformation? Well, I notice in the denominator, I have s plus 3 squared plus 5 squared. This is either going to be sine or cosine for both of these. All right. The reason why I know it's going to be sine or cosine is because I have 2 squares in the denominator separated by addition. And I know that either if the numerator is going to be s, that's cosine. If the numerator is going to be whatever this last value was, which we call k, this is k squared, then this needs to be k, the square root of this, which is 5. So that's why I put a 5 in, but I had to make sure that I put a 5 out. So now that I've changed it to make it look this way, I can now just use my inverse Laplace s minus a to go ahead and convert this. So this s plus 3 is really s over s squared plus 5 squared. Now, if I do this, then what I know is that that's just cosine. It's cosine of whatever this value is. So cosine of 5t times e to negative 3t, because it's s was s plus 3. So it's e to negative 3t cosine 5t times 2. On the right side, since it's 5 instead of s, it's going to be the sine function. So it's sine of 5t. E to negative 3t, because once again s plus 3 gives me the e to negative 3t, and then I have the 1/5 on the outside because I had to incorporate that 5.